The term units coordination describes the way students understand the organization of units as they approach problem-solving situations, and how their understanding influences their problem-solving strategies. In this episode, we're talking with Amy Hackenberg from the University of Indiana about how educators can recognize and support students at different stages of units coordination. Welcome to the podcast, Amy. I'm excited to be chatting with you today about units coordination.
Well, thank you for having me. I'm very excited to be here, Mike, and to talk with you.
Fantastic. So we've had previous guests come on the podcast and they've talked about the importance of unitizing. But for guests who haven't heard those episodes, I'm wondering if we could start by offering a definition for unitizing, but then follow that up with an explanation of what units coordination is.
Yeah, sure. So unitizing basically means to take a segment of experience as one thing, which we do all the time in order to even just relate to each other and tell stories about our day. You know, I think of my morning as a segment of experience and can tell someone else about it. And we also do it mathematically when we construct number, and it's a very long process. But children begin by compounding sensory experiences like sounds and rhythms, as well as visual and tactile experiences of objects into experiential units, experiential segments of experience that they can think about, like hearing bells ringing could be an impetus to take a single bong as a unit. And later, people construct units from what they imagine, and even later on, abstract units that aren't tied to any particular sensory material. It's, again, a long process, but once we start to do that, we construct arithmetical units, which we can think of as discrete ones. So it all starts with unitizing segments of experience to create arithmetical items that we might count with whole numbers.
What's really interesting about that is this notion of unitizing grows out of our lived experiences in a way that I think I hadn't thought about. This notion that a unit of experience might be something like a morning or lunchtime. That's a fascinating way to think about, even before we get to, say, composing sets of 10 into a unit, that these notions of a unit exist in our daily lives.
Yeah, and we make them out of our daily lives. That's how we make units. And what you said about a 10 is also important because as we progress onward, we do take more than one as a unit, like thinking of 4 flowers in a row in a garden as a single unit, as both one unit and as 4 little flowers, means it has a dual meaning, at least. We call it a composite unit at that point. That's a common term for that. So that's another example of unitizing that is of interest to teachers.
Well, I'm excited to shift and talk about units coordination. How would you describe that?
Yeah, so units coordination is a way for teachers and researchers to understand how children create units and organize units to interpret problem situations and to solve problems. So it originated in understanding how children construct whole number multiplication and division, but it has since expanded from just that to be thinking more broadly about units and structuring units and organizing and creating more units and how people do that in solving problems.
Before we dig into the fine-grained details of students' thinking, I wonder if you can explain the role that units coordination plays in students' journey through elementary mathematics and maybe how that matters in middle school and beyond middle school.
So that's where a lot of the research is right now, especially at the middle school level and starting to move into high school. But units coordination was originally about trying to understand how elementary school children construct whole number multiplication and division, but it's also found to greatly influence elementary school children's understanding of fractions, decimals, measurement, and on into middle school students' understanding of those same ideas and topics, fractions, ratios and proportional reasoning, rational numbers, writing and transforming algebraic equations, even combinatorial reasoning. So there's a lot of ways in which units coordination influences different aspects of children's thinking and is relevant in lots of different domains in the curriculum.
Part of what's interesting for me is that I don't think I'm alone in saying that this big idea around units coordination sounds really new to me. It's not language that I learned in my pre-service work and also in my practice. So I think what's coming together for me is there's a larger set of ideas that flow through elementary school and into middle school and high school mathematics. And it's helpful to hear you talk about that from the youngest children who are thinking about the notion of units in their daily lives to the way that this notion of units and units coordination continues to play through elementary school into middle school and high school.
Yeah, it's nice that you're noticing that because I do think that's something that's a strength of units coordination, and it can be this unifying idea, although there's lots of variation in what you see with elementary students versus middle school students versus high school students versus even college students. Some of the research is on college students' units coordination these days. But it is an interesting thread that can be helpful to think about in that way.
Okay, with that in mind, let's introduce a context for units coordination and talk a little bit about the stages of student thinking.
Yeah, so one way to understand some differences in how children up through, say, middle school students might coordinate units and engage in units coordination is to think about a problem and describe how solving it might happen. So here's a garden problem. Amaya is planting 4 pansies in a row. She plants 15 rows. How many pansies has she planted? There are 3 stages of units coordination, broadly speaking. We've begun to understand more about the nuances there, but a stage refers to a set of ways of thinking that tend to fit together in how students understand and solve problems with whole numbers, fractions, quantities, and multiplicative relationships. It's sort of about a nexus of ideas, and that we tend to see coming together, and students don't usually think in a way that's characteristic of a different stage until they've made a significant change in their thinking, like a big reorganization happens for them to move from one stage to the next. So students at stage 1 of units coordination are primarily in a ones world, and their number sequence is not multiplicative. That's going to be hard to imagine. But they can take a group of ones as one thing, so they can make a composite unit. And that means in the garden problem, they can take a row of pansies as one row as well as 4 little ones. And they can continue to do that over and over again. And so they can amass rows of 4 pansies and keep going. And what it usually looks like for them to solve the problem is they'll count by ones after any known skip counting patterns. So in this case, they might be like, oh, I know 4 and 8, that's 2 rows, 9, 10, 11, 12, that's 3 rows, often using fingers or something to keep track or in some way to keep track, and continue to go up and get all the way, barring counting errors, to 60 pansies. And so for them, the result, 60 pansies, is a composite unit. It's a unit of 60 units, but they don't maintain the structure that we see at all of the units of 60 as 15 fours. That's not something, even though they did track it in their thinking, they don't maintain that once they get to the 60. It's really just only a big composite unit of 60. So their view of the result is very different than an adult view might be. So the students at stage 1 can solve division problems, which means if they get some number of pansies and they're supposed to make rows of 4, they can definitely do it. They can solve that. But they don't think of multiplication and division as inverses. So let me say what I mean by that. If they had this problem next, so Amaya's mom gave her 28 pansies, how many rows of 4 can she make? A student at stage 1 could solve that problem, and they would be able to track 4s over and over again and figure out that they got to 7 4s once they get to 28. But then if immediately afterwards a teacher said, well, so how many pansies are there in 7 rows of 4? The student at stage 1 would start over and solve the problem from the beginning. They wouldn't think that they had already solved it. And that's one telling sign of a student operating at stage 1. And the reason is that the mental actions they engage in to do the segmenting or the tracking off of the 4s and the 28 pansies are really different to them than the ways of thinking they use to create the 7 rows of 4 and make the 28 that way. And so they don't recognize them as similar. So they feel like they have to engage in new problem solving to solve that problem. So to get back to the garden problem, students at stage 2 have a multiplicative number sequence. So they think of 60 as a 1 that they could repeat. Iterating is a term we often use. They could imagine it just being repeated over and over again. And this is a contrast to students at stage 1 who think of 60 as like, ooh, I got to have all 60 pansies there. if I'm going to think about a number like 60. Whereas students at stage 2 do have a multiplicative number sequence. And so they think, oh, I don't have to have all my 60 pansies. I can just think about one pansy and I just repeat it however many times I need to have however many pansies I want to imagine in my problem solving. So they anticipate 60 as 60 times. And that's obviously a great relief for kids who are dealing with big numbers. Like you can imagine it feels really onerous to think about 1,000 if you feel like you have to have 1,000 items in your mind. Oh, how could I possibly do that? But, I don't have to have 1,000. I can just have one and I can repeat it. That's a great economy, efficiency in thinking that happens. So in the terms of the garden problem, students at stage 2 also have constructed a row as a thing to count. So a composite units, one item as well, so 4 little items. And they can amass 4s, just like I was talking about with students at stage 1. But what they are also able to do is break apart 4s as they go along. They might say, well, I've got 4, and 4 is 8, and 1 more is 12, and 1 more is 16, and 1 more is 20, and 1 more is 24, and 1 more is 28. Maybe at that point they say, oh, let's see, I don't know what 1 more 4 is, but 2 more is 30, and then 2 more is 32. So they can take the row apart. They don't all do this, but they can. They have the mental capabilities to do that because they're not right in the midst of making the coordination happen. They're sort of a little bit able to stand above the coordination and take their rows apart if they need to.
It sounds like part of what happens at stage 1 is you might have a kid who potentially could count by 4s, for lack of a better way of saying it. And they might say, well, 4 and 4, so 2 sets of 4s, 8. And then at some point, it kind of breaks down where that memorized list of what happens when you count by 4. And then kids are back to saying like, okay, 12, 13, 14, 15, 16. And if you were watching this, listeners, you would see that I stuck out 4 fingers. And then I'm like, okay, so that's 3 4s and so on. And so I would see a student who might appear to be thinking about units, but tell me if I'm correct in thinking that it's more a function of that they know a set of numbers in a counting sequence for counting by 4s.
So students at any stage may vary in the skip counting patterns they know. I call it knowing a skip counting pattern, to know automatically like 4, 8, 12, 16, or whatever it is. So you could have a student at stage 2 who doesn't know their skip counting patterns very well. And you also could have a student at stage 2 who counts by 1. So that's the issue there, is you can't always tell just from what you see if you have to do more than the test of what I'm saying. It's just to give a sense of the stages. But the main thing is the outer boundary of what they can do at stage 2 is they don't have to count by 1s. They can do other things because of the fact that their composite units have this special feature where they're multiplicative in nature. I mean, the fancy term for it is they have iterable units of 1. But let me say a little bit more about what happens when they get to 60. So let's say a student at stage 2, they've gotten up to 60, there are 60 pansies and there are 15 rows of 4. They will think of the 60 as 15 4s as they make it. So we call it a 3 levels of unit structure. 60 is a unit of 15 units, each containing 4 little ones. They'll think about that way as they solve the problem. But as they continue to work further and like add more pansies on or do a further extension of the problem, they wouldn't maintain that 3 levels of units structure that we see. So that's important because it has implications for how they can build from what they've done.
How would you know that they hadn't maintained it? Like, what might they say or do that would give you that cue?
Well, so you see it most if, let's say, I say, oh, guess what? We got 12 more pansies and you're going to put them in rows of 4. Can you put those on? And then they put them on. Okay, they find out it's 72 now. Okay, so how many rows are we talking here? Like, it would be a new problem for them to figure that out. It wouldn't be like they would be able to maintain that, I had 15 rows and then I now have the 3 more added on.
Got you. Okay.
So you see they're having to remake stuff that as adult learners we would think, you should already know that that's 15 4s, right? But they'll have to redo that in solving an extension of the problem like I was talking about there. So students at stage 3, they also can definitely take 4 as a row of 1 and also 4 pansies. They can arrive at 60 and view it as a unit of units, but they also can view it as a unit of 15 units, each containing 4, and they maintain that. So if they were asked a further problem like, hey, we're going to rearrange this garden, we're going to actually put 3 rows together at a time. Can you do that? And how many rows would you have? And how many pansies in each row? And what would be the total? They'd be able to say, oh, yeah, I can, let's see, put my 3 rows together. That's going to be 12. And then I'm going to end up with 5 of them. And now they've created 60 as a unit of 5 rows, each containing 12. And they can still think of 60 as a unit of 15 units, each containing 4, or 15 rows, each containing 4. So they can switch between different unit structures. It doesn't mean they automatically know it without thinking it through, but they can do it and they can go back and forth. And that has great implications for anticipating and for solving division problems and seeing them as inverses of multiplication and a whole lot of stuff. Proportional reasoning, fractions, lots of things.
I think what's really interesting about this is I really appreciate you walking through the mental processes or maybe even the mental scripts that the kids might engage in to help see behind the curtain, for lack of a better word. Because what strikes me is that there is a point, probably early in my teaching career, where I would have attended and focused mostly on, did they get the answer? And I think what you're helping remind me of is that it's the how, but there are particular ideas. And now I think I understand why the notion of units, plural, units coordination matters so much, because a lot of what's happening is their ability to coordinate a unit made of units and then to be flexible with the units within that unit of units. Am I making proper sense of that, Amy?
Yeah, for sure. That's great. That's exactly it. So the process and what units get created and how they get thought about and used is actually really, really important in trying to support kids' multiplicative thinking, among other kinds of thinking too.
I think this is a great segue because I suspect that a lot of teachers are wondering about the kinds of tasks or practices or questions that they might use that could nudge students' thinking regarding units coordination. And I'm wondering, what are some ideas you'd recommend for teachers as they're trying to think about how they assess but also advance their students' thinking when it comes to units coordination?
That's a great question. And I mean, the big response is have students engage in lots of reasoning with units, composite units, breaking apart numbers strategically, thinking about different solution pathways. So not just one solution pathway, but can you come up with multiple solutions for the problem? Really sharing student solutions that involve breaking apart units, so if you're doing something like 5 sevens and finding out that kids are thinking of it as 5 fives and 5 twos, let's share that. How else could we break apart the 5 sevens? 5 fives and 5 twos, why is that maybe helpful compared to other ways we might think about it? Because we might know 5 fives and 5 twos more easily than other ways of breaking it apart. And then even how are kids thinking about the 5 twos and the 5 fives and evaluating each of those? So, basic things like that are super important. How many rows can we make with 36 flowers with 4 per row? Thinking strategically about that, like I know that 5 fours is 20 and I need 16 more flowers. So that's 4 fours because it's double 2 fours, so 8. So that means 9 rows total. So I'm just kind of really briefly talking through, but posing these kinds of tasks and then asking for how students can break them up and think about them and presenting and making public that kind of thinking and reasoning. So valuing it in that way and sharing it. Same thing with lots of even more advanced multiplication problems. So for example, my daughter's in 4th grade right now, and so we've been working with her on like 30 times 20 and doing something other than knowing 3 times 2 and then putting zeros on because she doesn't remember that. So to do 30 times 20, we asked her about 10 20s. Oh, she can figure that out. That's 200. And then can I iterate? Oh yeah, another 10 20s, another 10 20s. And then we did like 40 30s, which was definitely harder. And so as part of the process of that, after she figured out, 10 30s, when she was iterating her 30s, that was harder than iterating the 20s. She had to break apart numbers. Like when she got to like 90 plus 30, she had to think about 90 plus 10 plus 20. So doing embedded breaking apart of units with the prospect of, trying to figure out a larger multiplication problem is super important. And, interestingly, she could do 900 plus 300 and figure out that was 900 and 100 to get 1,000 and then 200 more. So that's additive reasoning, but it's the breaking apart of units and reconstituting them that's what's really important in the process of solving multiplication and division problems. So that's my big thought about that. And the other thing is to not go to patterns too soon. I mean, this is related to what I just said about not thinking that, like, I can just do 3 times 2 and then add zeros and count the zeros, because that really doesn't develop. It misses so much in what you can do with units. And so even if some kids do remember that and get the answer right, they're really robbed of the experience that we're trying to give to my daughter of really thinking about, well, how can I figure out 40-30s or 30-40s or 30-20s? Right now, I'm a big advocate of actually doing lots of counting by decade numbers, because I feel like it's a way of really enhancing kids' work with larger multiplication.
I've been sitting listening to you talk about this, Amy, and there are multiple things where I'm like, I need to ask her about this. I need to ask her about that. I need to ask about this other thing. So I'm going to ask you a couple follow-ups. One of the things that is just an observation is the language you used when you were talking about your work with your daughter. When the original task was 30 times 20, and you shifted the language to say 30-20s. And then you step back even a little bit from there and you said, well, what's 30-10s, right? This language that you were using, I wonder if you could be explicit about what you think that shift in language accomplishes.
Yeah, I've been also thinking a lot about this, so it's great. Yeah, one of the problems with multiplication notation is that it doesn't make clear anything about what the group is and what the number of groups you have are. And so just saying 30 times 20, I mean, you can think of that as 30-20s, or I can think of that as 20-30s, but the language doesn't contain it, so it doesn't like refer to the action I might do in thinking about how to actually figure it out. And kids have to bring a lot to the table then to really read that into that multiplication notation. It's even more so with fractions. I can say more about that in a second. So I really am advocating with my pre-service teachers is that we speak in iterative language with the multiplication. So we try to always say, like, I'm talking about 5-7s, or I'm talking about 7-5s, 30-40s, 40-30s. And then, of course, with the decade numbers, knowing that we can go down to like 10 of something and that's easier to figure out. And then we can build on that. So like 10-20s, and then, I'm going to need 3 of those 10-20s to get to 30-20s.
Which really, to some degree, is helping them make meaningful sense of the associative property as well.
Right. Yeah, exactly. It's very mathematically rich. Unfortunately, it's not necessarily worked on a lot, I am finding. And I think it's a real missed opportunity, because I think there's a lot that kids could do with that would really build strong meanings for multiplication and strong ideas of base 10 as well.
Yeah, absolutely. I think one of the things that I've been obsessed with lately is this notion of nudge or small-sized shifts in my practice that I can make. Part of what I'd like to mark for the audience is the shift in the language, as you described, 30-20s or 5-7s. Those are moves that a teacher could make to help clarify the fact that units are involved and help students visualize with a bit more clarity what's going on. That feels like something that a teacher could take up and really have an impact on students' understanding.
Yeah, I think so. I think it is something that is reasonable. And what's nice is it also can flow right into fractions, because then instead of saying just 3/5, we say 3/1/5. 4/1/5, 5/1/5, 6/1/5, 7/1/5. It allows for fractions larger than 1 to have maybe more of an iterative meaning. Not that that's a simple thing at all. That's a whole nother podcast we could do, but I've done a lot of research on that. But
Well, I think you're hitting on something important though, Amy, because this notion of what is a unit fraction, it's really 4/5 is a group of 4/1/5, right? And that's a critical understanding that I think often floats underneath students' understanding in ways that if we could make that clearer or help build that understanding, that also has huge ramifications for what comes later in their mathematics learning experience.
Yeah, so I'm a big proponent of iterative language there as well.
You have me thinking about something else too, which is the importance of context and having students deal with measurement division problems specifically as a way to build their understanding. And I know I'm using language right now for the audience that might not be super clear, but I'm wondering if you could talk a little bit about what measurement division means in context and maybe why that would be valuable for students.
Yeah. Right. So in multiplication and division structures, if we're talking about equal groups, there's always some number of equal groups, some number in the equal group, so a size of the group, and then a total number of items. And so with measurement division, we know the total number of items and we know the number of items in a group, but we don't know the number of groups. So my example of you've got 36 flowers and you want to put them in rows of 4 would be a measurement division problem because we know that there are 4 in each row and we know we have 36, but we don't know how many rows we're going to make. And so those are really nice to pair with work on equal groups multiplication problems because they are very closely related. And for kids, they can become closely related as they solve them and realize like, oh, I can use my multiplication strategies to build up my 4s and find out when I get to 36. And then I know how many rows I've made. So it's highly linked to what we're talking about here.
What I found myself thinking about is that in solving that problem, one of the ways that a kid could do that is they're iterating a set, right? So potentially they're iterating a set of 4s multiple times, and then they're finding out how many of those sets of 4 they have, right? So I think part of what you're helping me think about is the way that the structure of a measurement division problem maybe shines a flashlight on this notion of groups and the number in each group, and also some of the ideas you were talking about earlier with units coordination.
Yeah, for sure. And in terms of continuing the theme of using iterative language, then when you get the result of that problem, 9 rows, what does that 9 mean? It means 9 4s make 36. So that's a meaning both for 4 times 9 equals 36 as well as 36 divided by 4 equals 9. So it's nice to emphasize that. And yeah, as students build those meanings and have repeated work with that kind of thing, they usually often, we don't know all the mechanisms here, but they usually come to be able to at least make that coordination in their problem solving activity and ultimately make it so they can anticipate it like we were talking about with stage 3.
One of the things that is really helpful is in the course of this interview, we've talked a lot about what might the behavior of a student at stage 1 or stage 2 or stage 3 not only look like, but what might it mean for how they're thinking. And I think what I'm really appreciating about this, Amy, is there are a few practical things that an educator could do to support students. One is iterative language, as we've been talking about, and the other is measurement division, using a particular problem structure like measurement division to shine a light on these parts that we think are really important for kids to attend to if they're in fact going to make some of the shifts that we're hoping for.
Yeah, for sure. And then, also exploring the boundaries of what the kids' strategies are and asking for multiple solutions because you might see kids, even students at stage 3, that might be counting by ones. And so you want to, can you solve that another way? Is there another way you can do it? And so seeing what they see as possible, what they're able to think about is also really important to support units coordination.
Absolutely. Before we close, I typically ask a question about resources or training or learning experiences that would help someone who's listening continue learning or continue to think about how they could take up these ideas in their practice. You particularly, I know, have written some work around this, and I also suspect that you might have some recommendations in terms of organizations that can help educators really dig into these ideas if they saw that as something that was important for their growth. Would you be willing to talk a little bit about resources, organizations, or even the types of experience you think support teachers as they're making sense of all of this?
Yeah, well, yes. I was planning to talk about Integro at this point because Integro Numeracy Solutions has a lot of great supportive materials for all this kind of work. And everything that I'm talking about is something that is sort of built into much of what they do. For people who are unfamiliar, it's a council, it used to be called a council, of people who got together and have really developed materials that are supportive of teachers, working one-on-one to support students who might be struggling, as well as whole group instruction, all around developing strong number sense. And it's a very well-developed set of materials, both for classroom use as well as for teacher development. And we, meaning me and my 2 co-authors, Andy Norton and Bob Wright, wrote a book in the series for teachers on fractions called Developing Fractions Knowledge. And that was published, 9 years ago now. So Andy and I are working on a second edition right now. And in that book, we address units coordination and talk about its usefulness for teachers. It's mostly, though, a book about fractions and about how units coordination is relevant in trying to support students' fractions knowledge and to help assess students' thinking and also promote their learning. So that is one resource I can recommend on units coordination, with a revision coming in the next year.
That's fantastic. So I'll say for listeners, we'll include a link to Integro Numeracy Solutions if you want to check out the organization. And Amy will also add a link directly to the book so that if someone wanted to dig in and explore that way, they had the option. I think this is probably a great place to stop, although I certainly would love to continue. I want to thank you so much for joining us. It's really been a pleasure talking with you.
Yeah, likewise, Mike. I've really enjoyed it, and I look forward to further conversations.
This podcast is brought to you by the Math Learning Center and the Meyer Math Foundation, dedicated to inspiring and enabling all individuals to discover and develop their mathematical confidence and ability.